So no questions? All right. Well, let me give you a little starter uh, introduction, if you will, to chapter seven. So if you're looking at chapter seven, for instance, I've actually pulled the textbook open, uh, the ebook open to specifically sections, chapter seven, the opening part. The chapter is called Work and Energy. And we have Satchel Paige making a pitch on the mound from a very old photograph. And the sections are work done by a constant force. 7.2 is the scalar product of two vectors. So we're starting to build up our tools set for vector analysis and vector calculus and vector algebra, that sort of thing. Section 3, 7.3 is work done by a varying force. That actually is more of us contributing to our toolbox. In this case, it's actually a vector calculus tool called a path or line integral. So we're going to teach you a little bit about that. The good news is uh, I would say maybe 75 to 90% of all students have made it through Physics 241 and 242 without really knowing what the heck a path or line integral is. And that's the beauty of it. You can actually make a lot of careless mistakes and still get the right answer, but I'm going to try to teach you so that you won't. And then finally, section 7.4 is kinetic energy and the work energy principle, uh, which we'll be using. For instance, the most typical application of that is in if you wanted to analyze a crime scene, or should I say a crime scene, a wreck scene. For instance, when two cars are about to collide, it's very common if both drivers are alert enough, they'll hit the brakes. Prior to anti-lock brakes, there would be a long skidding that would occur, and police officers would then go out and measure the length of the skid. And the length of the skid, if you take what the make of the car of the vehicle is, you can get a rough estimate of roughly what the normal force will be. If you know a little bit about the tires, and you don't even have to know that much specificity about the tires because they don't vary hugely from one tire to the next in material, nor does the road vary hugely from one material to the next in terms of constants, coefficients of friction. But either way, you can find the normal force for the vehicle and you can find the work done by friction. And lo and behold, that work done by friction will be equal to the change in kinetic energy. And since you go on the assumption that the wreck ended in basically the vehicle coming to a velocity of zero, you can say the final kinetic energy is zero. Therefore, the change in kinetic energy, which again, we're going to introduce that quantity to you as well, the change in kinetic energy will just be equal to the initial kinetic energy, or actually the negative of it. And that negative of the initial kinetic energy is equal to the work done by friction, which is also a negative quantity. And that can allow you to figure out, for instance, the velocity of the vehicle prior to the skid. So that's one of the, often techniques used by police officers, state troopers, things of that sort after a wreck. The bigger picture of what's going on here is a whole different type of paradigm from the way we've been solving physics problems until now. So, for instance, we started off with kinematics, which is basically just an understanding of motion. If you're given, for instance, the acceleration, the initial velocity, uh, and the initial position, you can figure out at any time later, assuming all those things are exactly as specified, you can figure out any time later what the position is, what the velocity is, what the acceleration is, that sort of thing. And that's really helpful. And oddly enough, that particular part, kinematics, didn't care exactly what makes something accelerate, or, how do you get the acceleration that we assumed in chapters 1 and 2, for instance. How did you get that initial velocity? How did you get that final velocity, and that sort of thing? We didn't care about that at all in kinematics. However, once we got to chapter 3, where we introduced Newton's laws of motion, then we were starting to study the dynamics portion of mechanics. And the dynamics portion of mechanics is not only the kinematics part feeds it, but you actually can make some sense of it. In other words, you can say, well, what actually causes this object to accelerate? And Newton's second law tells us that. All of that, though, required us to use vectors. So we had to introduce vectors, we had to introduce normal force, we had to introduce tension, all those different things. They had quantities that had magnitude and direction. And it worked great, but that is quite cumbersome. So it'd be nice if we had another way we could solve physics problems where we didn't have to use vectors. And that's what the work and energy theme of chapter 7 and beyond is. Specifically, Samuel Maynard. I posted those and sent everybody. Sam is asking where did I post the video for chapter 6. I posted a couple videos on Canvas. I guess that was Monday when the power went out. I posted them and sent out an announcement and let everybody know that they were there. So, but at the same time, I also only put well, I don't want to say too much, but I tried to be very accommodating on face-to-face test two in case anybody didn't feel that comfortable about gravity. I'll leave it at that. And not only that, I'll tell you guys that the grading isn't necessarily finalized. So when I look back after everybody finally finishes their face-to-face test two, if I feel like I've done something that I don't think is fair to you guys, in other words, if I see a huge fraction of you guys not get the simple questions I have on gravity right, then I might actually adjust your score accordingly because I realized that was a problem that wasn't your making and it wasn't my intent. But yeah, that video is there. So going back to what we were talking about, the paradigm that we're doing in chapter 7 is a whole new paradigm where we don't use vectors. You can use vectors, and occasionally you might have to, break some vectors apart to figure out some parts or whatever. Or sometimes you can't get exactly the variable you want using these scalar methods, and therefore you might have to combine some facts about these scalars to make a new vector, and then that vector can be used to calculate something you need. So it's a little different, but the neat thing is, lo and behold, we find a new way of solving physics problems that doesn't involve vectors. Okay, the method is work and energy principles. So we're going to introduce a quantity called work, and what I want you to think about is the common definition of work. We use words like work and momentum and stuff like that in everyday life, and we use those words as well in physics, but in physics they have a very specific definition. Uh, but the fact that we use them tells us that there should be some kind of ringing similarity between the words that we use in everyday life and the words that we use in physics. So, for instance, you've probably heard Dick Vitale or some other sportscaster talking about a particular sports team, basketball or baseball. It's usually in a basketball or football context, but they'll have the momentum. And we're going to learn what that is. That actually is not part of the work energy paradigm that we're going to deal with. We're coming back to that after we finish the work energy method. But there's also things like work. So you guys know that people go to work every day. They might work 8 hours a day, something like that. But you have a sense of what work means, and we are gonna tie that together to the common word in such a way that you have some understanding of what it means in the physics world. I'll tell you that work, we can sort of think of it as work is anything that will that can be used to drive a nail. Okay. Only I've got to put some caveats on that. So anything that can drive a nail can be considered a type of work. And the reason why I say that is in driving a nail, if you think about it, you probably think to some extent that it's hitting it with a hammer and then like it hits it and then the nail takes off and goes into the board. And if you're really good at striking a nail, that is a common occurrence. And like when I used to work construction, that was one of the things we went for. We normally expect 2 hits per nail, and if you have to do more than that, you're kind of an idiot. And it's not really that you're an idiot; it's just you're wasting time. So we try to be better than that. But in reality, except for those really upper echelon hits, a lot of times what happens is you hit the nail and the nail head and the hammer head come together, and then the hammerhead, because of its weight and momentum, tends to push the nail along through some distance. So if you think about work as the ability to drive a nail, you might think, well, maybe work has to be a force applied over a distance, and you'd be more or less right. So that's the scenario I'm going with. It's work supplied over a distance, and you can do things like, let's think about mowing the grass. That's obviously a form of work. When you mow the grass, you're going to take a lawnmower that has a certain width, maybe 24 inches, or if you're in a country area, you might have a 52, 55, 65-inch lawnmower or whatever. And what you do is you could imagine, for instance, going north and south straight like this with the width of your lawnmower, which is maybe 24 inches, and then you get to the end of that swath and you turn around and come right next to it, another 24 inches, and then you turn around there and go right next to it. And what you'd see is for a really big yard, uh, you would basically say if the yard is, let's say, 240 feet wide, then 24 inches would be 2 feet, and that means you're going to have to make 120 passes. So one, two, three, four, five, six, seven, eight, till you get 120, and then you have done the full width of the yard. Now you might think, what about the depth of the yard? So the width is 240 feet, and obviously the depth of the yard matters as well. For instance, if you have a yard that's 240 by 100, then you're only going to have to travel 100 feet roughly on each path. So you do 100 feet, turn around, do another 100 feet, turn around, do another 100 feet. And that gives you some idea of basically how much work it would take. Now, if you start to think about it that way, could anybody tell me which would take more work? A lot that's 240 feet wide by 100 feet deep, or a lot that's 240 feet wide by 200 feet deep? And you can type that answer or just spit it out if you know it. Okay, so what I'm trying to get you to see here is since I introduced the concept of work and I said work is anything that can drive a nail, and then I explained to you that driving a nail usually requires a force applied through a distance, then the lawnmower, uh, being you pushing it, okay, that's a force you're putting in, and you pushing it 100 feet is quite a bit different than you pushing it 200 feet. In fact, it's twice as far in the 200-foot case. So I would argue that it seems reasonable that if I had a 240-foot yard by 100 feet, and then I had a 240-foot yard by 200 feet, the 200 foot yard would be twice as much work. And I think that's just, what you'd all reach the conclusion of, like if you went out to bid to mow a lawn and you told somebody that you'd mow this 240 by 100 lawn for $50. If someone asked you to come mow the grass of a different lawn that's 240 by 200, you probably lean towards maybe saying, okay, but I'm going to charge you $100 because it's twice as much work. So by doing that, we immediately think that work is directly proportional to distance, and you'd be right. That is actually one of the criteria for work. Another thing I could ask you, for instance, is what if you're pushing that 24-inch wide lawnmower, uh, to mow the grass, but you also have another version of a 24-inch wide lawnmower, but that other 24-inch wide lawnmower actually has really big wheels on it so that friction is not quite as much of a problem. Uh, Dents in the ground is not quite as much of a problem. And not only are the wheels bigger, but it's actually a lot lighter. So let's say instead of a 100-pound lawnmower, you're working with a 50-pound lawnmower. I would suspect that you would probably say doing it with the 100-pound lawnmower is about twice as much work as doing it with the 50-pound lawnmower. In that sense, if you reach that conclusion, we'd make the conclusion that work is probably proportional to the force. And that's really it. That's exactly how we start off. Work is proportional to the force you apply, and work is proportional to the distance through which you apply that force. So that's enough to get us started. Anybody have any questions on that? Okay, when we get to the energy part, there's going to be a neat mathematical thing that I can tell you where basically if you can show that one of these facts is true, then automatically a whole list of other facts are true, and that allows you to make a lot of conclusions about the problem you're solving and stuff like that. And that whole realm of problems are what we call conservative forces. and they're not like political conservative. They're also not like, Jimmy Carter telling us to leave the heat down and put on a sweater at night. So he's not talking about saving electricity. It's actually conserving in the sense of a zero sum game. So what I normally tell my students when I talk about a zero sum, I'm saying the word zero hyphen sum. When I talk about a zero sum game, I usually use something along the lines of payroll for Tidewater Community College. So, Tidewater Community College, for instance, let's pretend that their budget for payroll is $100,000, and let's say we have just 100 teachers. And let's pretend that's all the employees, because it really doesn't matter too much. But we're obviously way more than that. But just for concreteness, we can leave it focused on the teachers. So what that is, if we were sort of a socialist state, we'd immediately say, okay, well, everybody's going to get exactly $100, or excuse me, $1,000 a year, because we have $100,000 fund for paying the salary, and we have exactly 100 people. Therefore, 100,000 divided by 100 gives you 1,000. So each person makes $1,000 a year. Obviously, these numbers are completely made up for convenience, but the key point is they're made up for convenience. Okay, so now what happens if I go to the president and I say, I do a lot of work here. I go out and I do, physics demo shows, and I do astronomy shows, and I do observatory shows. I'll take telescopes out to distant places. I'm really doing a lot for the college, and I'm going to tell the president that I really think I should make $2,000 a year instead of $1,000. And if I could convince the president of that, then the president would say, "Okay, Mr. Younger, I'm going to go ahead and give you $2,000 instead of $100,000." Well, a zero sum game means now my win, my going from $1,000 a year to going to $2,000 a year, is your loss. That's what we mean by zero sum. So if one person profits, the other person has to, by default, lose. Okay, that's not the way nature works in general, but in some cases it does. When nature behaves that way, nature is conserving some quantity. In this case, it's conserving money. Specifically, there's only $100,000 and there's 100 employees. And if one of us are cocky and try to take twice as much, then that only leaves $98,000 for the remaining 99 employees, which means those employees are going to get on the order of $990 a year instead of the $1,000 they used to get. So that's a zero sum game, and that's exactly how energy conservation works. It turns out that there's a bunch of different types of energy. There's kinetic energy. Notice the word kinetic. That sounds like or kinesiology, or some other words that you probably heard. I'm using the word kinesiology because you've probably heard of kinetic tape or kinesiology tape or something like that. You're seeing a lot of athletes nowadays wearing some weird looking tape patterns on their body. I'm not convinced that there's really any good science to that, but I will tell you that is something that's being done, and it doesn't matter too much whether there's good science behind it. What matters is if the athlete feels like they get an advantage, or they feel a little more comfortable or less stressed because they have that tape on them, then they're going to do it. So, what I'm saying about this kinetic part is kinetic is basically a phrase from Greek that means motion. So when I say something has kinetic energy, that's the energy of motion, and we'll find out that the quantity kinetic energy is 1/2 times the mass times the square of the velocity. Now, that's true in the Newtonian world, but it's quite a bit different when we get to the relativistic world. So just remember that that's going to be a little bit different once we start to reach speeds that are on the order of 1% to 10% of the speed of light or higher. Then we're going to have to use different formulas for kinetic energy. But that's one of the forms of energy, is kinetic energy. There's also a type of energy called potential energy, and potential energy is the type of energy that has the potential to do work. That's a way of thinking about it, and it's often considered a energy of position. So, for instance, you've probably heard the seemingly cruel adage of if you find a turtle sitting on a fence post. The story is normally if you find the turtle sitting on a fence post, you're pretty confident the turtle didn't get there on their own. That's not really the part I'm speaking relatively here or relevantly about. But what is relevant about that is when a turtle is on top of a fence post, they're not very comfortable. and they have the potential to do work. And what I mean by that is if the poor turtle were to accidentally get knocked off the top of the fence post, then immediately upon falling from the fence post, this is a big blood blister, by the way. That's that weird mark I keep seeing. But immediately upon falling off, what happens is the potential energy, which is a measure of energy based on its position, which in this case turns out to be only relevant to how high the turtle was. But immediately when the turtle starts to fall off of that fence post, then their height decreases, and that means their potential energy is decreasing. But this is a zero sum game. So the potential energy decreasing must mean some other kind of energy is increasing. Well, guess what? That other kind of energy is kinetic energy. And the farther it falls, the higher and higher that kinetic energy gets. And then at the very end, just before it hits the ground, it's got its maximum kinetic energy, 1/2 mv squared. And that 1/2 mv squared is exactly equal to the potential energy the turtle had when it was sitting on top of the fence post. And not only that, as you see a turtle, flying down at some speed to the bottom of a fence, if you took a little nail and stuck it in the ground, just a little thin little nail, and just stuck the tip of it in the ground, if the turtle fell on that, he would drive the nail. Therefore, he has the potential to do work. So that's another way of thinking about it. So we're going to think about those sort of things. I'll tell you the kinetic energy I've already said is 1/2 mv squared. The potential energy, at least near the Earth's surface, is going to turn out to be just m, the mass, times g, gravitational acceleration, times h, the height above whatever you consider to be the zero potential energy. And just to further specify what I meant by the ability to do work, and the ability to do work is basically anything that can drive a nail. I want you to understand that when you go to try to assess whether something could drive a nail, you might have to imagine a nail that is maybe 1 atom in diameter. So it would be really, really thin and therefore very, very sharp, for instance. And you might have to consider that very, very thin nail being driven into, let's say, hot butter. Okay. If you're worried about the weight or the physics of the actual problem that you think might be doing work, and you say this is not enough to drive a nail into the ground or something like that, then you might need to reconsider a smaller nail going into a softer substance. Okay, so anything that can apply a force over a distance is something that is working. It's actually producing work. Okay, any questions on that? Now, all this is just words, so hopefully it gives you some sense of understanding from hopefully what you read. But in light of Sam's question, it seems like he might not have expected that Chapter 7 was coming tonight. So there's a good chance you probably haven't read Chapter 7 yet. And I think that's normal. Normally, what happens, I don't think my students are reading the chapters before I cover them. However, I do highly recommend that. You should probably read at least, the first 4 or 5 sections of any chapter before we cover them. And it's not going to be necessarily a positive experience for you. Your eyes are gonna glaze over and you're gonna yawn and stuff like that. So I wouldn't advise doing it for very long. Maybe do it in 5 minute intervals, 10 minute intervals. Take a break, come back, read some more. Take a break, come back, read some more. That sort of thing. But in doing so, it'll make you better prepared for lecture. And then if you read it again after you've covered that material, you'd be surprised how much more you know. So let's get started by sharing my iPad screen so we can work some actual problems. Okay, so we're going to share my iPad screen, and I'm doing things a little differently this evening because I've been working outside and handling a lot of different things, so I couldn't do the problems the way I wish to. Plus, that last video where I put a extensive amount of work in to writing a bunch of questions, and then all of a sudden this program lost all of my problems is ticked me off to no end. So I'm not inclined to do that again. So hopefully I won't get in trouble for copyright violation. If not, if I do, I'll just empty the or just erase this video. But anyways, let's start off with example 7.1. Work done on a crate. So I want to remind you guys, we reached the conclusion that work is directly proportional to force, and work is directly proportional to the distance over which the force is applied. So you can sort of think of as work as force times distance. And you know the units of force are, anybody recall what the unit of force is we use in this class? Feel free to type it or just spit it out. Figuratively, of course. Might be named by a person. There you go, newtons. Yes, capital N are newtons, named after Isaac Newton. And remember the Newton exactly. Adrian just posted kilogram meter per second squared. He got some. Oh yeah, he did S asterisk S. Very good. Yeah, that is the definition of a Newton, by the way, is a kilogram meter per second squared. So when I say work is supposed to be force times distance, we know the unit of force is the Newton, and the unit of distance would be the meter. So evidently, the unit of force would be or excuse me, the unit of work would be force unit times distance unit, which would be a Newton times a meter or a Newton meter. Well, that's exactly it. And in fact, that's so convenient. We've gone a little farther and went ahead and defined 1 Newton times 1 meter is exactly equal to what we call 1 joule, Joule, with a capital J. And that too is another person's name. In fact, if you've been to Great Britain, you might have run into a beer called Jowls. And that beer Jowls was created by the Joule family that's quite famous for thermodynamics and heat engines and work and energy and all this good stuff. So that's actually the origins of that name Joule. So now that we have all that behind us, let's look at this example. It says work done on a crate. A person pulls a 50 kilogram crate 40 meters along a horizontal floor by a constant force FP equals 100 newtons, which acts at a 37-degree angle as shown in figure 7.3. The floor is rough and exerts a friction force F sub FR equals 50 newtons. Determine A, the work done by each force acting on the crate, and B, the net work done on the crate. Okay, so we're actually going a little farther. I've gotten you started on what we need to understand about work, and that is specifically only that work is proportional to force and work is proportional to the distance over which the force is applied. But it's actually more than that, because it turns out that sometimes when you apply a force to an object to make it move, part of that force that you're doing is not helping you at all. And in some cases, it's actually harming you. So, for instance, if you've ever seen a small child cutting grass compared to an adult cutting the grass, what you occasionally see, and I'll try to stand up here, what you occasionally see when the child is mowing the grass is something along the line. I have to do it with one arm because my left arm's not working right now. So you'll see the kids sort of down like this, their heads tucked, and that sort of thing. And the actual railing, the handles for the lawnmower is normally pushed all up forward and stuff like that, and they're digging through the ground. Whereas an adult can just walk like this and they're holding on to the handle, everything's good. Well, what's happened is the kid has normally, if they're doing like that, the kid has sort of worked out physically that it's easiest for them to push the lawnmower in that particular position, specifically because when they do it that way, their arms are almost perfectly horizontal, and therefore the force that they're applying is essentially perfectly horizontal. And that's generally what they're trying to do. I mean, unless you're cutting grass up a mountain or down a mountain or something, you are trying to force the lawnmower to go horizontally. So any component of force that's not horizontal is wasted. So because we're big adults and we're usually tall enough to actually push the lawnmower from above, and we actually push at a downward angle like this, we're actually wasting a lot more energy in doing it that way than the child would be by pushing it horizontally, because a good fraction of the force we apply to the lawnmower is actually perpendicular to the path. So I have a new thing for you guys to think about when we say work is equal to force times distance. What we mean is really work is equal to the component of force that is parallel to the actual path that you push the thing. So again, remember, work is something that can drive a nail, and that requires a force acting through a distance, Okay. What we're saying now is it's a little more complicated than that. We only want the component of force that's parallel to the path over which you're walking, or pushing, or applying the force, or whatever. Or another way of looking at it is you could say, I only want the component of the vector that dictates you basically points from where you were to where you will be. Okay, that one displacement vector. If you only take the component of the displacement vector that is parallel to the force, then that's another way to calculate the work. But we normally don't do it that way. It's just another option, and you'll see that when we talk about the dot product. So now we've got a little bit more complicated formula for work. Work is force parallel times distance. So let me go ahead and get out of the world of speaking and give you what we've reached, what conclusions we've reached. So we found that work is directly proportional to force times distance, but it turned out that it wasn't quite that. It actually turned out that work, W, is equal to force, and then I'll put these two little bars by it. That means parallel times distance. But you could also write that as D parallel times force. Okay, so in other words, you'd have to render the displacement vector, which is a vector that points from where you started to where you stopped. And if you took a component of that that happened to be parallel to the force and multiplied that by the whole force, then you'd get the right answer for the work. Okay, so the more advanced version is not work equals FD, but work is equal to F parallel times D, or work is equal to D parallel times F. And what we'll learn is that dot products in vector algebra have been created for just such an application. Whenever you need to find a component of a force that happens to be parallel, or excuse me, more generally, whenever you need to find a component of a vector that happens to be parallel to another vector, the dot product is what you use. Another word for the dot product is the scalar product. So we're going to get to that. We'll cover it in a second. And we've also got to soup this up a little bit more because it turns out it has to be a little bit more complicated to decide. But now that we have that, let's go ahead and work. So part A, they said the work done by each force acting on the crate. So what we have here is, as you can see from the free body diagram, you have the summation of the forces in the y direction equals mass times acceleration in the y direction. But in this case, we're not expecting this box to jump up and down. It's pretty much going to have the same height all the way along, sliding along this floor while we're pushing it. So in this case, the acceleration in the y direction is equal to 0. And from the diagram that they've drawn here, it looks like we have Fn, which points in the positive direction, plus negative mg, which points in the negative direction. Hence, I wrote the negative there. Notice I'm taking time to write the plus and then the minus sign again, just to get back to where we were. That's brief. Okay, I'm not going to do that. I'm normally going to write it F normal minus mg, but I just did it for this time. Now we also have other forces. Now the force of friction is completely horizontal, so there's nothing there. But that FP actually is a vector that has a component parallel to the motion, and it has a vector that's parallel to the y-axis. So we need that component of FP that's parallel to the y-axis. And you can see from here, if we're treating the right as positive, then the x component of that force would in fact be pointing to the right, and the y component of that force would be pointing upward. So those are actually the two components that we'll need, and we can go ahead and use our trigonometry to say that this force FP, oops, I wrote a B instead of a P, FP has a magnitude equal to 100 newtons, and it has an angle of 37 degrees. And what we're going to say is that, sorry, I drew that in green. I was going to use green to point in the positive direction and red to point in the negative direction, but I'll just stick with blue pointing in the positive direction and red pointing in the negative direction. So we can see that's the two components of force, those two blue ones. The one down here is FP sub x, and the one up here is FP sub y. And from our knowledge of some old horse came a hopping through our alley, or so ka toa, whichever one you want, we know that the sine of 37 degrees, which equals opposite over hypotenuse. And remember, the hypotenuse is the one that the little right angle sign looks like an arrow pointing towards. So opposite would be FPY, and the hypotenuse would be 100 newtons. You could also say that cosine, which is adjacent over hypotenuse, cosine of 30 degrees is in fact equal to adjacent over hypotenuse. And remember, adjacent is the side that's actually touching the angle but is not the hypotenuse. The hypotenuse, of course, is always the longest one. It's also the one that's opposite the 90-degree angle. It's also the one that the 90-degree angle symbol sort of looks like an arrowhead pointing towards. So in this case, we're going to say it's F P sub X over 100 newtons. Now, if you recall, the 37 degrees is part of the 345 triangle, so you don't actually have to even use your calculator here. Just remember that when you have the 37 degrees, then the opposite side is the smaller one, so that has to be the 3. The adjacent side is the larger one, and then the hypotenuse is 5. But since our hypotenuse is 100, we can multiply 5 by 20. But if I multiply 5 by 20, then 3 needs to be multiplied by 20, and 4 needs to be multiplied by 20. So we get 100 for this one, we get 60 for this one, and we get 80 for this one. So we can immediately tell that, for instance, the x component of FP is going to be 80 newtons, and the y component of FP is going to be 60 newtons. That way I don't have to use the calculator or trigonometry or anything like that, or remembering anything. So now I can go ahead and say the summation of forces in the y direction is Fn, that was pointing up, plus negative mg, that's pointing down, plus Fp sub y, and we just learned that Fp sub y is going to have to be 60 newtons. And then that's all the forces that are acting on it. Remember that I mentioned this before. I want to reiterate it. When you're going to draw your free body diagram, you got to make sure you count all the forces. The forces are all uh, corresponding to what the object you're drawing the free body diagram for, what is it touching? So everything that that object is touching has the potential to put a force on it. So you need to go and check each force. So for instance, the object here is that wooden crate. That wooden crate is touching the ground. So there must be a force associated with the ground. And of course, we know that's the normal force. It's also touching whatever is supplying the force FP, which could be a person with their arm pulling it, or it could be a rope tilted up at 37 degrees through which they're pulling. But the main thing is something is physically touching the wooden box. Therefore, there should be a force associated with that. Now, once you've taken everything that's touching it and thought of all those forces, then you've got to think of these sort of magical forces. And these magical forces are forces that we call our action at a distance. In other words, one of the big things when Newton discovered gravity was that Newton knew there was a little bit of a problem. Specifically, it was as if the sun was reaching out across space and pulling on the earth without physically touching it. That's called action at a distance, and it was something that bothered him. But he knew with his discovery of the 1/r² law for friction, he could solve a lot of problems and understand a lot of stuff. So he just put that on the back burner and said, maybe later on we'll figure out exactly how this action at a distance works. But for us guys, when we're actually doing free body diagrams, we have to consider those action at a distance forces. In 241, you pretty much only run into gravity. So gravity, which results in weight, which is equal to mg, is one of them. In principle, though, it could be a magnetic force, or it could be electric force. It could be a strong nuclear force. It could be a weak nuclear force. Those seem to be the existing forces that we know of in nature right now. And all of those sort of, in some sense, act at a distance. So when you're doing a free body diagram, check everything that's touching it, make sure you have a force associated with each thing that's touching it, and then check your action at a distance. Now that we've done all that with this particular free body diagram, we can see that all of the forces acting on the box have been taken into account in the y direction. Notice I did not include the force of friction, but that's because that's acting in the x direction. So I'm going to set this equal to 0 because m times a is 0 since a is 0. And immediately this tells us that the normal force is going to be equal to mg minus 60. Now, the mg turned out to be a 50 kilogram crate multiplied by g, which is 9.8, and 50 times 9.8. Obviously, 100 times 9.8 would be 980, so this must be 450. Okay? Oh, excuse me. 480, excuse me. All right? I hate doing arithmetic in my head. That's always a careless mistake waiting to happen. So, anyways, when I take 50 times 9.8, I get 490 like this. So the normal force is going to be 490 newtons minus 60 newtons, which equals 430 newtons. So that's the normal force, which we don't necessarily have, but when it asks specifically for the net work done on the crate, what we have to do is consider each force in turn and calculate the work done by it. So the normal force is a potential force to do work, so we might need that. Now that we have it, we could also use it, of course, in calculating the force of friction. But in this case, they actually gave you the friction force. They didn't give you the coefficient of friction, which normally, once they give you the coefficient of friction, you've got to use the coefficient of friction multiplied by the normal force to get the friction force. Okay? All right, so we've got that satisfied. So we now know all the forces acting in the y direction are the normal force, which is 430 newtons, the weight, which is 490 newtons in the opposite direction, and the 60 newtons is a upward directed force that's a result of the FP being applied at 37 degrees. Now I'm going to do the same thing for the summation of forces in the x direction, only in this case, I don't necessarily have to do anything with the summation of forces in the x direction. That would be us using Newton's second law and vectors to calculate the actual acceleration and various things like that. We're not doing that. We're asked to calculate the work, so I just need to identify all the forces. The rest of the forces are shown. We have the force of friction is 50 newtons. We have mg is 490 newtons. We have Fn is 430 newtons. We have Fp is 100 newtons. So we're good to go. Now we're going to use our force, or excuse me, our formula for work to kind of compute what the work done by each force acting on the crate is. So in A, it says determine the work done by each force acting on the crate. So if I say the work done by friction, or excuse me, the work done by FP, I would call that W sub FP, and that's going to be the component of FP that happens to be parallel to the motion times the distance. And if you remember, it said the distance we're going to travel is 40 meters. So I'm going to go ahead and write the component of FP that happens to be parallel to that blue vector. Everybody see the blue vector X that says 40 meters? Notice that points in the positive X direction. So what component of FP, now that I've shown you specifically, I've shown you up here exactly what the components of FP are, which component of FP is actually parallel to that blue vector? Anyone? Okay, so the blue vector is it's horizontal and therefore pointing in the x direction. So clearly we want the x component of FP. The x component of FP we figured out is in fact 80 newtons. So I'm going to go ahead and write, whoa, for starters, I'm going to get rid of my laser pointer and I'm going to write 80 newtons. and that's the component of FP that happens to be parallel to the vector x. And of course, the length of vector x is 40 meters. Now, they gave us 40 meters only to what we assume is 2 sig figs. They actually gave us the FP to 3 sig figs. So, in principle, I could write 80.0, but once you multiply it by 40, you're back down to 2 sig figs, anyways. So, 8 times 4 is 32, and that leaves 3200. Which remember turns out to be Newton meters, but that's also equal to 3,200 joules. And technically, it's not acceptable to assume the zeros are sig figs. So I'll underline them that way. So that's the work done by the FP. Anybody have any questions on that one? I don't know what just happened, but I lost stuff. Okay, there it is. Okay. So that's one of the forces, and that's the work done by it. If you wish to calculate, for instance, if you wanted to dig a little deeper and maybe you didn't understand some of the nuances of this problem, you might think, oh, well, there's a FP sub x, and then there's a FP sub y, so I need to calculate the work done by FP sub x, and then I have to do the work done by FP sub y, and then I have to do the work done by Fn, and then if Fn had a component that's parallel to the x-axis, I'd have to do the x one and the y one, but in this case, I just only have to do Fn. If you were to take that route by mistake, okay, what you quickly realize is that when you try to calculate the work done by the y component of FP, what you'd see is the y component of FP is exactly perpendicular to the travel distance, to the vector of displacement. So there's going to be no work done to that by that one. Okay. Now, what about the work done by gravity? Same sort of thing happens. The work done by friction, however, is quite different. So let's do the work done by friction. Oops, I should probably stick to red or blue, excuse me. Work done by friction. So your book is calling friction F sub FR. The work done by friction is the component of friction that happens to be parallel to the x vector times, again, the distance. I'm writing D here just because I wrote D up top. I probably should have been using X since your book, since the actual problem showed X, but I think y'all are getting what I'm saying. In this case, notice the component of friction that is parallel to the motion is actually the only part of the friction force, and in fact, it's anti-parallel. So what that really means is this one is actually fighting. In other words, the friction force is this way and the displacement is that way. And that is sort of like thinking of it as it's doing the opposite of helping. So the way we account for that, and you'll see when we do the dot product, it automatically works out this way. But the way we account for that is we say that the force is actually uh, acting in the negative direction, so you end up getting a negative amount of work. So in this case, what we're going to do is we're going to take the friction force and we're going to put a negative in front of it, but we're going to write 50 newtons. And again, the negative in front of it is because you can think of it as the force is in contradiction to the displacement. Because it's literally going the opposite way. So whenever you have a force going one way and the displacement going exactly the opposite, that work is going to have to be a negative quantity. Okay. Now the displacement is again 40 meters. So again, we're looking at only 2 sig figs. But in this case, we have 5 times 4 is 20. And then we add the 2 zeros on it. So it's going to be 20 times 20 with a 0, 0. So that's 2,000. And we get negative 2,000 newtons. And of course, sig fig rule, or excuse me, joules. The sig fig rules tell us that we're only allowed to have one of those zeros, and that's going to be joules. So now we're going to say the work done by friction is, in fact, negative 2,000 joules. Any questions on that? The work done by the friction, or excuse me, by the normal force is the normal force that happens to be parallel to the displacement vector x, which we're calling that distance d, times d. So now that I have the force of the normal vector that happens to be parallel to d, I think you can realize that there's no component of the normal force that's parallel to d. So we actually have to write 0 newtons times 40 meters equals 0 joules. So that's another thing to keep in mind when you're calculating work. If you have a force that's completely perpendicular to the displacement, it can't do any work. So anytime you apply a force and that force is perpendicular to the displacement of the object, then automatically the work done by that force will be zero. So we're learning all sorts of cool stuff. Now we can also do the work done by mg. So in this case, I'm going to say work done by gravity. That, of course, is mg parallel to x. So I'd write it like that. But again, the mg, the component of it that's parallel to the blue vector is zero. So this is just going to be 0 joules is equal to work done by mg. Does that make sense to everyone? So our forces were the friction force, the normal force, the weight due to gravity, and FP. And now we've done the work due to, or we've calculated the work done by each of those four forces. And that was what part A was about. So I'm just going to write an A right here so we'll know. Now part B says the net work done on the crate. The net work means add them all up. It's just like your net pay is, your hourly rate times your hours minus FICA and all that good stuff. So you have to do all the additions and subtractions. That's what we mean here. So the network is going to be adding them all up. And that gives us work net equals the work done by the friction force, or excuse me, by the normal force plus the work done by the friction force plus the work done by the FP plus the work done by mg. Now you can see what happens when we add all those up. We're basically just going to get 1,200 joules equals W net. Anybody have any questions on that one? All right, Adrian asked me a question a bit earlier, so I want to follow up with that. It says, so it's force parallel because of the contact with the surface. I don't really understand. I tried to read it when you popped it up there, but I might have seen it after I made some point that made what you wrote understandable. You think you could articulate that a little better for me, Adrian? The applied force is parallel. Oh, and if the applied force is parallel, then you just do the force times the distance. If it makes an angle other than 0 degrees with it, then you take the component that's parallel. Or in some sense, you might often have the component that's anti-parallel, in which case you have to get a negative for the work done. Again, once I show you the dot product, that'll give us a good reason for putting that negative in there, as opposed to me just telling you it's like an ad hoc solution. Okay. So let's move on to the next one. I'm checking the results. Yes, I got the same results as the book did for example 7-1, so that's good. Now we're going to do another problem. This is problem 7-2. It says, A, determine the work a hiker must do on a 15-kilogram backpack to carry it up a hill of height h equals 10.0 meters as shown in figure 7.4a. Notice I only included figure 7.4a, by the way. Determine also B, the work done by gravity on the backpack, and C, the net work done on the backpack. For simplicity, assume the motion is smooth and at a constant velocity, i.e. acceleration is 0. So a lot of times we have to do that. Let me take a sip real quick. My mouth's getting dry. So a lot of times when we're doing work problems, we have to imagine a process going so slowly because we only want exactly enough force to overcome whatever's trying to make it not move, say. So we're trying to consider just the bare minimum force that will allow something to begin accelerating, but not so far that it actually accelerates. So that's what's going on here. That's why they're saying, for simplicity, assume the motion is smooth and at constant velocity. Okay. If it wasn't at constant velocity, then the force would be a little bit bigger than ma. The net force would be a little bit bigger than ma, and that would uh, require us to have some of the work going into creating a new type of energy, kinetic energy. So we're not interested in doing that. So how are we going to do it? Well, we're going to draw a free body diagram for the backpack because that's the thing that has the forces acting on it. I'm going to go ahead and draw a coordinate system like this. This will be my x-axis. This will be my y-axis. The backpack is going to be this little guy right here. And what we know is the mass of the backpack is equal to 15.0 kilograms. So we immediately know one force that's acting is the weight. So I'm going to go ahead, since it points in the downward direction, that's a negative direction according to my coordinate system. So this is going to be mg, which is equal to 15 times 9.8. And that's 3 sig figs in both cases. So this is going to be 147 newtons. That's the actual weight. Now, in addition to that, we've got the force applied by the backpacker. So we actually are going to, or by the hiker. So we'll call that force FH. And what we're doing here is we're assuming the force that the hiker is applying is just enough to more or less counteract the mg. So we've got those two forces acting vertically in such a way that it's not going to accelerate. So that means the summation of the forces in the y direction has to equal zero. So in this case, I'm going to draw green for the positive direction. And this happens to be the force due to the hiker, which we call F sub h. Now, in addition to this, we're going to have the displacement vector, which we generally do not draw on a free body diagram. But the key thing here is I'm just trying to show it to you so that we can make use of it for the calculation of work. Remember, work has to be the component of force that is parallel to the displacement vector. So in doing that, what I'm going to do is try real hard not to make you think that this is a force or anything like that, but I'm going to draw it as a dotted vector. So that's our displacement vector. And in this particular example, the textbook is calling it D, whereas the last one they called it X, but it doesn't matter too terribly much. Now, what we do know is, according to the diagram, this distance from here to here is H. And we don't know what the horizontal distance is, but we do know that this angle right here is what they're calling theta. Okay? And that's going to be relevant because what we have to find is the component of force that's parallel to that displacement vector D that I just drew. Okay? So what we can think for a second is let's draw the green vector as a sum of two components. One component will be parallel to the d vector and the other component will be perpendicular to the d vector. That is actually fine. We can work it out that way. Not necessarily the same way the book does it, but it would work. The same thing with the mg. We could make a component of mg that is parallel to d. In this case, it'd actually be anti-parallel to d. And we could make a component that's perpendicular to d. So if I were to do that, I might want to draw them them in, some other color. So let me just show you what they would look like. What we would have is this FH component parallel to the actual displacement would be that little purple vector, and perpendicular to the displacement would be this purple vector. Now, in addition to that, we would have I'm going to go with a neat new color. I'm going to go with this crappy baby poop orange color. Okay. What I do here is I treat the vectors parallel and perpendicular. So the mg would have this component that is sort of the component of mg that's parallel to the displacement. You can see it's technically anti-parallel though. Notice it points in the opposite direction. And then we also have this component that's perpendicular to mg. So you can actually use those components to compute the work in each case, or you can look at this geometrically and try to figure out exactly how this component parallel to D is related to the angle theta. So let me go ahead and show you right now in terms of the angle theta. We can see that theta is the angle between the D vector and vertical, and then that means the angle between the blue x-axis and the black line, this angle right here, that's got to be 90 minus theta because this makes a right triangle. And this is 90 degrees, and these other two have to add to be 90, so this one must be 90 minus theta. This one, on the other hand, is actually 90 degrees, so that means this angle has to be theta. So now I can go ahead and write in and say we know one of the angles and how it's related to these components. Specifically, this little angle right here is theta. Okay. Now, you might not be as easy, or it might not be as easy to find how theta relates to the mg vector, but we can do that as well because we know, for instance, this angle is 90 minus theta, and notice they're across a vertex from one another, so this angle and this angle are identical. So this angle is the same as that angle. They're called vertical angles, vertical, and it doesn't mean they're up and down or anything. It means that they're angles that are across from a vertex from each other. Example being, if you just draw two lines like this angle equals that angle because they're vertical angles. But this angle is also equal to this angle because they're also verticals. So that's just some geometry that we assume you know because you're in a physics class. Okay. You might be like me. Like I was not awesome. I was a horrible student, so I didn't get the chance to take geometry when I was in high school. So I'd never, in fact, to this day, I still haven't had a formal geometry course. I did get to teach it in high school for a brief period, but I never had one. So that's okay. That's just something you got to work through if you haven't had it. So now that we figured out that, we know, for instance, this is 90 minus theta and this is 90 minus theta. This is theta, or excuse me, this angle right here is 90 degrees. And since this is 90 minus theta, this angle must be theta. So that's theta right there. I'm going to go ahead and draw a little arrow and say that angle is also theta. Now, because of that, we can now compute exactly what the work done by each of those forces are, and I'm going to do it as follows. So first off, for part A, we're saying determine the work the hiker must do on the 50 kilogram backpack to carry it up the hill of height h equals 10 meters. So I should go ahead and finish that out. That's 10.0 meters. So we have that. We have a displacement, which is that whole hypotenuse of that hill there, but we don't know that, but hopefully it'll work out. So let's look at part A. The work done by the hiker is work done by F sub h, and that equals the component of F sub h. I didn't draw that F very well. It's the component of F sub h that is parallel to the displacement vector times the distance or the length of the displacement vector. Well, we can see from this triangle right here, okay? See that triangle? If FH is the actual force that the hiker is putting on there, then it's this hypotenuse here. We want this little bit, and what we can see is that if we take the cosine of theta, we get this little bit divided by the hypotenuse. So that's what we got to do. I'm going to write that as, uh, let's say, cosine theta is equal to FH parallel, because that's the adjacent side, divided by FH, like that. So we can now write FH times the cosine theta. So I'm going to say FH times cosine theta. Now I just have to multiply that by D. But this is kind of neat. It turns out if we look at this other triangle, the one that we see right here, you can see that D times cosine theta is in fact equal to H. So D cosine theta is just H. So the FH parallel uh, times D just becomes FH times H. And that should make some sense. Let's go ahead and compute it, and I'll talk that out a little bit. So we now have basically the work done. Oops, I was supposed to be writing this in blue. We now have the work done by the hiker is equal to FH times H, and the FH has to be a very specific quantity. Now, remember, I said the acceleration has to be zero, so now we can figure out what that quantity is. The summation forces in the y direction equals mass times acceleration in the y direction. And the author and the problem, of course, already told us that all the accelerations are zero. So in this case, what we know is FH minus 147 newtons is equal to zero. So we know FH is equal to 147 newtons. So now we can plug that in. Oops, I meant to stay with blue. 147 newtons times H, which is 10 meters, gives us 1,470 joules. And of course, we only had 3 sig figs, so that zero is not correct, or it's not a sig fig. So the work done by friction in this case is 1,470 joules. Notice what we did conclude. By working out the geometry, we found that the component of FH that happened to be parallel to the displacement turned out to be FH cosine theta. But cosine theta times D also turned out to be H, so we can just write FH times D, and that's what we did. So the work done by the hiker we've already solved as 1,470 joules, which we technically supposed to write as 1.47 times 10 to the third joules. I'm going to go ahead and write this off to the side and say the work done by the hiker is equal to 1.47 times 10 to the third joules, and I'll circle that off and I'll put the A next to it so we know that was the answer to part A. Part B, it says the work done by gravity. So in this case, we want the work done by mg. So we need the component of mg that's parallel to the displacement. And of course, that's the little diagonally down into the left one. And we can look at this triangle again to figure out what that component is. Let me go back and get that color that we were using here. This guy is the component of mg that's parallel to D. Okay. And you can also see that cosine theta, I'll write it here, cosine theta is equal to adjacent over hypotenuse, and the adjacent is mg parallel, and then over the hypotenuse is just mg. So yes, I wrote that so small that you can't see it when I shrunk it down to the normal height. But let me write it again so we can figure out what it was. So that's the mg that's parallel. Now we have that, and we can go ahead and calculate that the work done by gravity. So I'll call this work mg. I could also call it work W with a capital G as a subscript, or W with a lowercase g as a subscript. All of it doesn't matter. But now I'm going to take the work, or excuse me, the force mg, but I'm going to take the component that's parallel to D, and then I'm going to multiply it by D. So in this case, we see that the mg parallel to D is actually just mg times cosine theta. But remember that mg parallel is actually anti-parallel, so I have to force that negative. Again, once we cover the dot product, we'll be able to do this without forcing that negative in there. But right now we have to do it this way. So that's the mg parallel to D. Now I've got to multiply that by D. So again, what we learned was cosine theta times D is actually equal to H. So now we can write negative 147 newtons times 10.0 meters is equal to negative 1470 joules, but we're not allowed to count that zero as a sig fig. So the work done by gravity is actually the opposite of the work done by the hiker. That's going to be something that's really relevant later when we learn about the work energy theorem. So we can now say that the work done by mg is equal to negative 1.47 times 10 to the third joules. And that, of course, is part B. For part C, they want to know the net work done on the backpack. So we have the only forces acting are FH and mg. So really the net force is just work done by FH plus work done by mg, which is obviously going to be zero. So for part C, I'll say W net is equal to the work done by the hiker plus the work done by gravity, which equals 1,470 joules plus negative 1,470 joules, which equals 0 joules, equals W net. Okay. Well, it turns out that whenever you calculate the net work done on any system, the work energy theorem tells us that the net work done on any system is equal to the change in kinetic energy of that system. As we said, we were not wanting to accelerate this backpack at all. We were just wanting to move it at a constant speed. Therefore, the kinetic energy, which is 1/2 mv squared, doesn't change at all. Therefore, we exactly expect this result, which is that the net work done was 0 joules. Anybody have any questions on that? All right. Well, we've been going for an hour and 20 minutes. So let's go ahead and take 10 minutes, give you guys a break here. And I'll sit here in case anybody has any questions, but we're going to start on the next section. Does anybody have any questions on this before we leave? You're welcome to ask them. But like I said, I'll be here the whole time, but we're going to come back at it's 6:46 now, so come back at 6:56. I'm good. Thank you, baby. I'm going to move to the next page. Uh, Anybody need me to keep this here before I do that? Got about 4 more minutes, 5 more minutes. Got about 2 minutes left. I'm worried about these headphones messing up my hair. Jackson, did these headphones mess up my hair? My nephew's here. All right, got about 1 minute left, everyone. All right, we're going to go ahead and get started. So, the question here, this is actually a conceptual question from your textbook as well. Specifically, your textbook says the following. It says the moon revolves around the Earth in a nearly circular orbit with approximately constant tangential speed. Uh, Kept there by gravitational force exerted by the Earth. Does gravity do A, positive work, B, negative work, or C, no work at all on the moon? So the big question here is does the force of gravity, which is obviously the force that keeps the moon orbiting our sun, or excuse me, orbiting our Earth, that is the force acting on it, then is it capable of doing work? I think what you can see is that at any instant in time, the displacement, remember displacement is the distance traveled, but it's specifically a vector quantity. So it actually has to be the velocity times the time, velocity being a vector quantity. When you multiply it by a scalar quantity, time, you just get a vector that's parallel to the velocity. And you see in my diagram here, I've drawn a picture of the Earth, which is the blue sphere, and then a picture of the moon, which is the gray sphere. And by the way, this is not to scale whatsoever. To give you some idea, if the Earth was about this big around, okay, it's about the size of this light bulb here. That's a little bit bigger than 2 inches. If I took and extended my arm all the way out to the right like this, and then I extended my other arm all the way out to the left like that, that's about, it's a little bit short, but that's about how far away the moon would be from the Earth. So this diagram is definitely not to scale, and you probably never seen the Earth Moon system to scale. But it literally is the distance from the center of the Earth to the edge of the Earth, or to the surface of the Earth, is one Earth radius, and we call that R with the little circle with a plus in it. And then the distance from the center of the Earth to the approximate average distance of the moon is 60 times that big. Okay, so you probably already saw that when you were reading over chapter six, or you heard me explain it when you watched the videos from chapter six. But either way, that's what we're looking at here. Additionally, the Earth is only, or well, the Earth is a little bit more than 4 times bigger than the diameter of the moon. So it's also not so to scale even comparing the two diameters. But the main thing here is we see that the force, which according to Newton's law of gravity acts along a line connecting the center of mass of the Earth to the center of mass of the moon. If you assume the Earth is basically a uniform solid, then obviously the geometric center of the Earth would be the center of mass of the Earth. And the same thing would be true if you make the same assumptions about the moon, that basically the mass is uniformly distributed throughout the moon. Then you'd find that the geometric center of the sphere that we're representing the moon with is the actual center of mass of the moon. So the force that Newton gave us, F equals G m1 m2 over r squared, where G is 6.67 times 10 to the negative 11th, that force has to act along the line that connects the center of the Earth to the center of the moon, essentially. Okay, so we see that that line is in fact, what we call a radial line. It points radially inward, and that means it's a radius. Okay, so if you imagine the orbit of the moon being an actual circle, then the F vector is parallel to a radius. So if you drew a line from the center of the Earth to the center of the moon, that would be a radius line, and the force has to be actually parallel to that, specifically pointing from the moon towards the Earth. Now, the velocity we know is, of course, perpendicular, or in some sense perpendicular to that force. But if you didn't see it was perpendicular, you'd at least know that the velocity was tangential to the circular orbit. And that's what I've drawn here. It says tangential. And of course, a line tangential to a circle is, in fact, perpendicular to a line that is radial. So when you multiply v, a vector quantity, times delta t, you get another vector that's parallel to v, and the force is perpendicular to v. So the force and the v times delta t is in fact perpendicular to one another. Therefore, the work done by gravity has to be zero. Now, in reality, the moon actually does not obey a perfectly circular orbit. It actually is a little bit elliptical. And for instance, you've heard of the supermoon, and that happens when the moon is actually at its closest to us during its orbit, a position called perigee. In that case, it'd be perihelion if it was closest to the sun, and aphelion if it was farthest from the sun. But when we're talking about something orbiting the Earth, which we call geo, then we'd say it's apogee and perigee. So, with all that in mind, hopefully you've reached a conclusion that the work done, if it's purely a circular orbit, is zero. But in reality, there is a little elliptical component to the actual orbit. It actually is sometimes a little closer, sometimes a little farther. Therefore, there is a little bit of velocity component at certain points in the orbit, or just about all the points in the orbit, where the velocity has a slight component parallel to the force. So you could, in principle, say that work is done in that particular portion of the orbit, and that's really the work being done in speeding up the moon for that brief period of time. And then once you get to its closest point, it's not going to get any closer because it's called the closest point. It's called the perigee, right? But from there on out, the velocity actually has a component that's, again, parallel to the force, but in this case it's anti-parallel because it points outward, and that's actually going to cause it to slow down. Okay, because the component of force, I might have said that backwards, but the component of force is now acting in somewhat parallel to the velocity, but anti-parallel, and it slows it down for the other half of the orbit. So the net effect is it does some work to speed it up till it reaches perigee, and then the force of gravity does a little work to slow it down until it reaches apogee. And then the whole process repeats itself. So even if you want to take into consideration the fact that the orbit's not circular, then what we see is the network in any one orbit is probably very close to zero. But at certain points, i.e., half of the orbit, it's going to be a very small amount of work done, speeding it up from perigee, or excuse me, from apogee to perigee, and then on the way back from perigee to apogee, it's going to do a little bit of work in slowing it down. That's a negative amount of work. So hopefully that helps. Anybody have any questions about that or the force of gravity? Since again, we sort of had to cover the force of gravity in absentia via my videos. So by all means, even if it's not this time, you ask next time, and I'll be glad to work any vector problems or any gravity problems for you guys. Okay. Any questions on that before we move along? All right. So, how are we going to use the tools of mathematics to find the components of force that are actually parallel to the displacement vector? So, we're thinking of work as a force vector quantity dot product with a displacement vector, again, a vector quantity, and that is a new version of the work formula. So, I'm going to call this section, it's called the dot product, but it's also called the scalar product. And in general, what we mean is if you have a vector A and you take a dot product of it with B, what you're getting there is there's a couple ways to do it, but I'm going to explain one of them first. It turns out to be the magnitude of A, which we can write as A vector with absolute value bars. You can also write double sets of absolute value bars. That's a more normal way, but either way is acceptable. And then the magnitude of B, and then the cosine of the angle between them. And this formula has to be accompanied by a diagram. So let me show you what I mean. I will say this vector right here is vector A, and I will say that this vector right here is vector B. And notice those two vectors are tail to tail, and that's important. I drew it that way on purpose. When the vectors are tail to tail, then the angle between them, the smallest angle, is theta. Obviously, there's another angle between them that goes like that, but we're talking about the smallest angle. Okay? So this diagram, A, B, with a theta in between them and their tail to tail, is absolutely necessary for you to apply to that formula. So if you're trying to use that particular formula, A dot B is equal to A times B times cosine of theta. Notice I can also write it this way. Then it doesn't make any sense to say the formula is AB cosine theta unless you have the diagram. Now, let me show you the power of this dot product and why I'm saying the things I'm saying. Remember, we're wanting to calculate work by taking a component of force that happens to be parallel to a component of the, or excuse me, happens to be parallel to a displacement vector. So if we could find some mathematical tool that just picks out the component parallel to another vector, that would be great. Well, that's what the dot product does. It's a little convoluted, but let me show you. So what we can do is I'm going to break up the vector A into a component that is perpendicular to B and another component that is parallel to B. In order to do this, I can draw that line right there and let that represent the line that's perpendicular to B. And now what I have is this guy right here. Oops. And that is the component of A that happens to be parallel to B. This is the component of A that is parallel to B. Now, there's another vector too, of course, and that would be this vector right here. This vector is the component of A perpendicular to B. So you might call this A perpendicular to B. Okay? Now, if you look at that right triangle we drew, I'll try to draw it again now. And trying to use the same colors and everything. This is the angle theta, and this is the component of A parallel to B. Okay. Now, what you can see is from this triangle, cosine theta is equal to adjacent over hypotenuse. So that's A parallel to B divided by the hypotenuse, which is just plain A. So what we see is A parallel to B is actually equal to A cosine theta. But remember the formula A dot B is equal to A B cosine theta, but we can also write that as B times A cosine theta, in which case you see that this quantity is in fact the component of A parallel to B. Okay, so if you were to take A dot B and just divide out the magnitude of B, you'd automatically get the component. So that's the usefulness of it. Not only that, it works both ways. For instance, we could draw the same diagram that we have right here. I could draw that again, but instead of drawing it with a perpendicular line that's perpendicular to B, we could make a line that's perpendicular to A. Let's see if I can do this. I'm going to copy, and I'm going to say paste. Mm, Why is it not letting me paste on it? Okay, it's just being a jerk now. Okay, let's just redraw it because it's not being helpful at all. Uh, I drew A this way. I drew B this way. And this is the angle theta. So all I really have to do is draw. It's kind of hard to do it in this case. Let me change the angle of that B, just that vector B, just a little bit, so to make it easier to deal with. So now drawing it like that, it's a little easier to make sense of. We'll say this is vector B. Now I'll draw a line perpendicular to A. Oops, didn't do this so well. That happens to touch the end of A, or excuse me, the end of B. Now with that, you can see that this part right here is actually equal to B cosine theta, but it's also B parallel to A. Okay, so you could also say A dot B is equal to A B cosine theta, and then this part right here is the component of B parallel to A. Okay. Now, if you really wanted to get fancy and actually do the whole mathematics of getting exactly what the component parallel to it is, there's a vector that you'll learn about in linear algebra. They call it the projection vector. And some notations you might use, for instance, is the projection of A onto B. And that means basically the component of A that's parallel to B. So the way we could do that is we could take A dot B because we know that gives us the component of A parallel to B, specifically the A cosine theta part, right? But in order to do that, we would actually want to divide out the B part. So I'll go ahead and take the magnitude of B and divide it out. So that makes, instead of us having AB cosine theta, now all we have is just A cosine theta. But we now have the magnitude of what we'd call the projection vector of A onto B, which you can sort of see it would be. Let's do this with a purple vector. The projection of A onto B would actually be on this guy. It's the same as that green vector I drew. I'm just trying to draw it again uh, while it's fresh in your mind to see. That is the projection of A onto B. And it's a vector quantity, right? So since it's a projection onto B, I need it to point in the direction of B. What I have by doing A dot B over B is basically just the magnitude of it, which is great. That's what we need for instance, for work. But I want an actual vector that points that direction. So what I might think is, wait a second, I could multiply it by v, but then by b, excuse me, the vector b is in boy, but then the magnitude would go up by, instead of it being just a cosine theta like it was when we divided by b, it would go back to ab cosine theta. So if I take the vector b and multiply it by that by this formula, and then divide by the magnitude of b, then that'll get rid of that extra b. So all I have to do is put a square there, and actually I didn't mean to write that in purple, so I'll put a square there and a b there. But notice the subscript, the lower the I'm looking for I was looking for subscript. That's the word. I was looking for a word. The subscript B is the one that appears the most in the formula, but that is an actual way of mathematically calculating a projection vector, which is a vector that points in the direction of the way it's written here. It points in the direction of B, but it's only as long as the part of B that would point in the direction of B, or excuse me, as a part of B, A that would point in the direction of B. So that's the projection vector. Either way, what we can now say is that work is going to be F dot D. As long as F is a force and D is a displacement, then F dot D works. But what we're going to discover is there's times when you go a little distance that's represented by itty bitty displacement vector D, and then the force changes. Maybe the magnitude of the force changes, maybe the direction changes, maybe both change, in which case uh, you've got to recalculate. But what if instead of it being just one straight line, what if you're actually doing some hoop to doop, sort of path? In that case, what you want to do is break the path up, which might be some wily S shaped thing or something like that. Break it up into small little straight lines, and if they're small enough, then what'll happen is the magnitude of the force over that whole displacement vector will not change enough for you to care, and the direction of the force will not change enough over that displacement vector for you not to care. What I mean by for you not to care, well, if you wanted the answer to 3 decimal places, then if the force changed just a little bit from one end of the little straight vector to the other end of the little straight vector, and you calculated it, but it didn't differ except in the 5th decimal place or the 6th decimal place, then you wouldn't have to subdivide the path any smaller. So you're going to take and imagine a curved path and break it up into little straight segments, and then you're going to apply the force at each of those little segments, and those segments should be small enough where the force doesn't change significantly. When we do that, it gets a little more complicated, and lo and behold, we get this formula. work is equal to the integral of f dot dl. Okay, so instead of a displacement vector d or x, we're imagining a path that goes, some crazy shapes like this. And what we're going to do is say, okay, we'll represent that by a little straight blue bit, and then another little straight blue bit, and another straight blue bit, and another straight blue bit, like this. And by cutting it up that small, the individual forces, which might have been little purple bits, should be roughly a constant at each of those values. And those are F's at different points, of course. And these little guys are the DLs. So there's a DL, there's a DL, so on and so forth. So this is actually how you compute work when the force could actually vary along the path and when the actual path itself varies. If it's just one straight line, then you might still have a force that varies and you could carry out this integration process, but it'd be a lot simpler process. So that is ultimately the answer we're shooting for. But now I got to show you some more about the dot product. So let me do this. I'm going to take and copy a page here. Copy page. So I can do more stuff with the dot product. And now I'm going to say paste page. And we'll paste it right after this. Okay, so now I have that. So we already have one formula. We found that A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. And we found that that could also be written like this. But it turns out it can also be written another way because you can say the vector A is equal to A sub x, meaning the x component of A, times the I hat vector, plus the component of A, the component of A in the y direction times the j hat vector, plus the component of A in the z direction times the k hat vector. And similarly, we could define the B vector as B sub x I hat plus B sub y j hat plus B sub z k hat. I'll show you an example with numbers in a second, but the main thing is we got to get through this part. So if we actually did a dot product, let me show you how you could work this out. And this method that I'm showing you here will come in super handy later because you're going to learn in this process that the dot product is something we call a linear operator. Which makes a lot of simplifications that can be done, and it just makes it a lot easier. So if I choose to calculate A dot B, I'm really doing some crazy stuff by putting all these different colors in here. By the way, you could also write this as AX, AY, AZ, and you could write this one as BX, BY, BZ, and that's just a lot less writing than having to do all those A hats, or excuse me, I hats, J hats, and K hats. Notice I use less than and greater than symbols instead of parentheses. So when you use parentheses, those are supposed to represent points, but if you use less than and greater than symbols to enclose those ordered triples or ordered doubles, then they represent vectors. Okay, so in this case, it's going to be AX I hat plus AY j hat plus a z k hat dotted with, I need b, sorry about that, b x I hat plus b y j hat plus b z k hat. Now, what does this mean? Well, it's the FOIL method. That's part of the reason I've told you guys that that stuff we learned in pre-algebra, the distributive property and all those things, those are fundamental tenets that we've used to define what we call an algebra. And whenever you find some things that have those properties, like we learned in pre-algebra, then that constitutes what we call an algebra, and therefore you can get a whole bevy of ideas about what vectors are and all sorts of cool stuff like that. So it's very common for us to go on the assumption that a dot product should behave just like one of those algebras. So we expect the FOIL method to work and all that sort of stuff. So what I'm going to do is let the first term hit the first term, and that's going to give me a sub x I hat dotted with b sub x I hat. Now I'm going to do the first term with the second term. So I can say like this one, and this is going to give me a sub x I hat dotted with b sub y j hat. And now I can do the third term, and this is going to give me a sub x I hat dotted with b sub z k hat. Now I've got to do the second term, so I'm going to say plus a y j hat dot b x I hat plus a y j hat dot b y j hat plus a y j hat dotted with b z k hat. Now I've got to do the third term, which is going to be a z k hat dotted with b x I hat plus a z k hat dotted with b y j hat plus a z k hat dotted with b z k hat. So obviously you had three-term polynomial with another three-term polynomial. When you multiply a three-term polynomial by a three-term polynomial, you get 3 times 3 are 9 components. That's what we got is the 9 there. Now, if we go on the assumption that this dot product is a linear operator, uh, what I mean by that, because I'm literally defining this for you right now, is that you can take the dot product and pull all the scalars through it that you want. So, for instance, I could take this AX and put it in here, or I could take this BX and pull it out here, and it wouldn't change at all. That's one of the properties of a linear operator. Basically, if you had a scalar times a vector plus a scalar times another vector, and you did a dot product with that, then the fact that the dot product is linear means you could bring out the scalar out in front and then just do a dotted with the vector plus the second scalar, bring that out in front and just dot it with the second vector. So that's kind of nice. And when you look at it this way, you can actually see that it's ultimately going to turn out to be. So again, I'm using the linearity property, and I'm going to write a x b x I hat dot I hat. So that's just from that first term. Plus I got a x b y I hat dot j hat plus a x b z I hat dot k hat. Notice that that makes some sense with the first row of the math I did immediately above it. I'm going to continue on. Plus AYBX J hat dot I hat plus AYBY J hat dot J hat plus AYBZ J hat dot K hat plus A Z B X K hat dot I hat plus A Z B Y K hat dot J hat plus A Z B Z K hat dot K hat. Okay. Now, You should be able to do this on your own, of course, but I wouldn't expect you to necessarily know to do it up front. But I'm showing you now, and you can watch this video as many times as you want. But what we've got here is enough for us to completely understand exactly why the dot product is what it is. Remember what we learned, that A dot B is equal to A times B times the cosine of theta. Does anybody recall what the magnitude of the I hat vector is? The magnitude of the I hat. Anyone? Yes, that's right, Beth. Yeah, and it's specifically one unit. It's not 1 meter, it's not 1 Newton, it's not 1 meter per second or anything. It's one unit. So the magnitude of the unit vector, or excuse me, of the unit vector I hat is one. The magnitude of the unit vector j hat is one. The magnitude of the unit vector k hat is one. So when we go to do the dot products, like this little guy right here, I hat dot I hat, this quantity is just 1 for the magnitude of I hat times 1 for the magnitude of the other I hat times the cosine of the angle between them. Those two vectors are identical. So what's the angle between them? I'm expecting Beth to answer, but somebody else might do it. Good job. Beth did answer it that way. So yes, it's the cosine of 0 degrees. And of course, 1 times the cosine of 0 is 1. So I hat dot I hat is equal to 1. When you do the same thing over here, though, it's quite a bit different. I hat dot j hat is 1 times 1. But can anybody tell me what the angle is between I hat and j hat? Good job. 90 degrees, Beth. And of course, the cosine of 90 is 0. So that means, oops. So that means that I hat dot j hat, just like I hat dot k hat, just like j hat dot k hat, and so on and so forth. Whenever they're different, you're going to get 0. Whenever they're the same, you're going to get 1. So now I can go through and make this a lot simpler by writing 0, 0, 0, 0, 0. But I can also go back and write this as uh, this one would be j hat dot j hat, so it's 1. And this one would be k hat dot k hat, so it's 1. So we ultimately get ax bx times 1 plus ay by times 1 plus az bz times 1. There's no reason to write those ones there, so it's just ax bx plus ay by plus az bz. So that's another formula for the dot product. So I'm going to go ahead and circle this one off too. So now we have two formulas for the dot product. And in fact, what's often done is if you have the two vectors in I hat, j hat, k hat components, you can go ahead and do the dot product, ax bx plus ay by plus az bz to get an answer. And then you can compute the magnitude of A and you can compute the magnitude of B, and then you can set AX BX plus AY BY plus AZ BZ equals the magnitude of A times the magnitude of B times the cosine of theta, and that allows you to find the actual angle between the two vectors A and B. So it's a really powerful tool to have because you can do all this stuff with it, which obviously includes projection vectors, making work with integrals and all sorts of cool stuff like that. But it also can give you some real geometry. Like we usually will take vectors to represent the distance and displacement from one atom to another within a solid. And then you can figure out what the angle is between the bonds between those two atoms and two other atoms by taking the dot product of the two vectors, one that points from the corner of a lattice to a center atom, and then another one that points from that same corner lattice atom up to a different corner. And you can find the angle between the bonds by doing the dot products and setting them equal to each other. So it's a really, really powerful tool. But just as a quick example, let's say A is equal to 1 I hat plus 2 J hat plus 3 K hat. And let's say B, I want to write this a different way just to save us some time. Let's say this one is 3, 7, 0. So A dot B, hopefully y'all can all see, should be 1 times 3 plus 2 times 7 plus 3 times 0, which equals 3 plus 14 plus 0, which equals just 17. She was just 17. So that's a simple example of how to calculate a dot product. Now, what if we wanted to know the angle between those two vectors? Well, we can say the magnitude of A is equal to 1 squared plus 2 squared plus 3 squared, which equals 1 plus 4, that's 5, plus 9 is 14. So it's going to be the square root of 14. Similarly, the magnitude of B is equal to the square root of 3 squared plus 7 squared plus 0 squared. So that's 9 plus 49, which equals 58. So it's the square root of 58, like that. So you can now say 17 is equal to the square root of 14 times the square root of 58. Obviously, we can make some simplifications with those radicals, times the cosine of the angle between them. And that tells you that the angle between them would be, I don't even have to make the simplifications, that's why I'm not bothering. I take 17, I divide it by parenthesis. Now I'm going to take the square root of 14. So I'll say 14. Now I'm going to say times square root of 58. So I just did, oops, I gotta press exit. Where to press my exit button? Hold on. I hit something. Now I can't find my exit button. Where's my exit button? Mm. Okay, that's not helpful at all. Maybe I literally am using a calculator that I can't find an exit button on, and it says to hit the exit button so I can get out of it. Mm, B, 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 B. Not there, not there. Oh, there it is. Okay. I'm going to delete that part. Maybe that would help. Anybody get an answer yet? My calculator's pooped the bed. Okay, I'll try it again. 17 divided by the square root. This is really a pain in the rear. Uh, Square root of 14 times square root 58. And now that, oh, finally. So I got cosine theta is equal to 0.596583. Now I'm going to take the inverse cosine of that, and that gives me 53.5 0.37 degrees. So that's a typical problem you should be able to do with dot products. Uh, that was just one I just made off the top of my head. Actually, it's several that I just made up off the top of my head. So hopefully that'll help you. Anybody have any questions on that? All right. Now that we have that, I've given you a little introduction to dot products. You have pretty much anything you need for dot products. The big thing to notice here is when I did the A dot B, I have 1 times 3 plus 2 times 7 plus 3 times 0. Notice there's no I hats, J hats, or K hats. For some reason, even though I show these examples all the time, my students will turn in an answer for a dot product and it'll have an I hat in it or a J hat or an I hat times a J hat. No, it's a scalar quantity, so it should only come out to be a number. So make sure you keep that straight. Anybody have any questions on it? All right. Later we'll learn a dot product, which does the same thing, except it gives a vector. So that's also called a vector product. And instead of it being AB cosine theta, it turns out to be AB times the sine of theta, which probably tells you, oh, that must pick out components that are perpendicular to other vectors. So that's exactly what it does. Now that we have that, let's try an actual problem. So it says using the dot product, the force shown in figure 7.7 has a magnitude FP equals 20 newtons and makes an angle of 30 degrees to the ground. Calculate the work done by this force using equation 7.4 when the wagon is dragged. So they're actually asking us to use work equals FP dot D, which I think you guys can see is right there. Okay. So what we can do is realize that FP is a vector. Let's do it this way. I'm going to say make a coordinate system. There's my x-axis. There's my y-axis. I have a vector that's going to be at 30 degrees. And the magnitude of that vector is 20 newtons. I'm also going to have a displacement vector. And that vector has a magnitude d that's equal to 100 meters. Notice I just wrote the d without the vector symbol over it. That's because I wanted to set it equal to the actual 100 meters. Similarly, this one I could just write as FP because I just am talking about the magnitude. So if we figure out what the x and y components of FP are, then we're good to go. So what I'll do is I'll say cosine 30 degrees is equal to adjacent over hypotenuse. So let me draw what that would be. That would be the adjacent side, and that would be the opposite side to 30 degrees. So this would be FP sub x, and this would be FP, oops, I wrote FB. This would be FP sub y. And what trig gives us from SOHCAHTOA or some old horse came a hopping through our alley is cosine is equal to adjacent over hypotenuse. So that's FP sub x divided by 20 newtons. And sine of 30 degrees is equal to opposite over hypotenuse. So that'd be FP y over 20 newtons. So we can now write FP as a vector. Oops, there I go, writing it as a B again. FP I can write as a vector by writing FP sub x I hat plus there I go again, plus FP sub y j hat. Now, according to my calculator, 20 times cosine 30 gives me 17.32. That's one extra digit, so 17.3 newtons I hat, and 20 times the sine of 30 degrees, which is obviously the y component, that gives me 10. So this will be plus 10 newtons j hat. We can also write the d vector because it is actually a vector. I don't know where this little thing to the left came from, but I don't know where that came from. Anybody? Whoa, still doing. Where's that coming from? Okay, evidently the world wants me to have it. All right, so now the D vector actually points to the right. That's horizontally in the positive x-axis direction. So this is going to be 100 meters times, oops, I wrote J, times I hat. So I can finally say work is equal to FP dot D, which equals, in this case, I'm going to say 17.32, or excuse me, 17.3, went too far, newtons times 100 meters plus 10 newtons times 0 plus 0 times 0 because neither one of them have any z components. So we see that the answer is just going to be 1.73 times 10 to the, in this case, it would be 17300, but we 17300, but we're using scientific notation, so it's times 10 to the fourth, and it's a newton times a meter, so it's a joule. Anybody have any questions on that one? All right, now quickly, I don't know what's going over here on the bottom, why it's doing this, but my program's obviously screwing up. So, work done on a spring. In this case, what we've already learned, or what we should learn, is something called Hooke's Law. We only got like 3 minutes, we only got like 5 minutes left. Hooke's Law says that when you apply a force, F, that on a spring or a solid object, stretching it or compressing it, that the length of that object will change by an amount x, and that's given by k times x. But the weird thing is the force will always point in the opposite direction of the stretch. So, for instance, if you're pushing to the left, which is the negative y direction or negative x direction, say, if you're pushing to the left on a spring, you could actually be compressing the spring and you're going actually in the negative x direction. The force will actually point in the positive x direction. So that's why the negative sign there is there. That's called Hooke's law. And what we're doing here is we're wanting you to imagine that we have just such a spring attached and we want to attach to a wall and we want to apply a force to it and calculate the work done. So it says a person pulls on the spring, figure 1710, stretching it 3 centimeters, which requires a maximum force of 75 newtons. How much work does the person do? The person is actually pulling the into the spring a distance x, and the force that the person's applying is in the same direction as the stretching. So those two quantities both have the same sign. What we're doing is realizing that, oh, it still must be a magnitude of force given by kx, but we're talking about a different force. So it's not F is equal to negative kx, it's F is equal to positive kx. So now I can go ahead and calculate work is equal to the integral of Fp dotted with dl. Okay. The force that we actually apply is k times x, and that's going to be in the positive direction. So I'll put an I hat. Then I got a dot product here. Now my dl, that is supposed to be a little path or a little part of a path that in this case is all along the x-axis. So you should throw out the l and replace it with x. So we're going to make the dl, which has to be a vector quantity. Notice it has a vector arrow over it. We're going to make that dx. And of course, it points in the positive x direction. So I put an I hat right here. Now, what we're doing is called a line or path integral. And technically, what you're supposed to do is you're supposed to let the DL direction point in the direction you're integrating, or let the limits of integration show which direction you're integrating, but not both. What you do in each case, though, is you choose one to point in the direction that you're going, and the other one just points in the positive coordinate direction. So if we use the limits of integration, for instance, to dictate which direction we're going, we would say we're going from x equals 0 to x equals 3 centimeters. And then by default, the DL would just be positive dx I hat. In this case, it'd be the same either way. If we chose to do the DL in the and use that to indicate the direction of integration, we'd use DL is equal to positive dx I hat. But by default, we'd have to go from small x to large x for the range of integration. So we'd integrate from 0 to 3. So you'd see you get the same answer in both cases. That's why the vast majority of the time students never learn how to do line integrals or path integrals, even completing this whole course. I'm trying to show you how more specifically for bigger goals. So now that we do this, we can go ahead and use the property of linearity that I just taught you when we were doing when we were doing the dot product. It's going to be the integral of kx dx. So I just use the linearity of the dot product to pull all the scalars out in front, and then I have a I hat dot I hat. And I'm integrating from x equals 0 to 3.0 times 10 to the negative 2 meters, because I have to have it actually in centimeters or in meters, not centimeters. So, and it's actually, yeah, 3.0. So now we can do the integral of kx dx. Of course, I hat dot I hat is just 1, so that disappears. So we get 1 half kx squared, and we're going to integrate it from x equals 0 to 3.0 times 10 to the negative 2. But that's the ultimate formula. It turns out the work done in compressing or stretching a spring is equal to 1 half kx squared, where x is the amount of compression or stretching that you did of the spring. So we did a sort of a derivation of that just now, and we solved the problem. In this case, we actually have to figure out exactly what the K is, and we already know that because it says required a maximum force of 75 newtons to move it 3 centimeters. So we can say 75.0 newtons. Ooh, actually, it wasn't supposed to be 0.0. 75 newtons is equal to K times 3.0 times 10 to the negative 2 meters. So K is actually equal to 75 divided by 3 times 10 to the negative 2 gives me 2,500. And that's newtons per meter. So we can now go ahead and say 1 half of 2,500 newtons per meter for K times, now we're going to do 3.0 times 10 to the negative 2 meters squared minus 0.0 meters squared. So we say 0.5 times 2,500 times 3 times 10 to the negative 2, square that. That gives me 1.125 joules. Now, obviously, we only had 2 sig figs, so we should call that 1.1 joules, and hopefully that's good enough. Anybody have any questions on that? All right, so we've completed enough. I didn't get as far as I wanted. I will tell you that the work energy theorem is just delta K is equal to W net. So this is enough to get you started on the homework. And K is equal to 1 half mv squared. So delta K would be 1 half mv final squared minus 1 half mv initial squared. So that's what goes on the left-hand side. W net is what we calculated 3 times already. So hopefully that's enough to get you guys started, and I'll finish this up next time. You're free to go. Thanks for coming. Thanks for being attentive and interacting. I'll wait till the last person leaves in case anybody has any questions. Yes, if you want to go ahead and chat me your first and last name, that's cool. Let me know, for instance, that you're in the asynchronous class RNO2B. That's fine too. Uh, but like I said, you guys are free to go. All right, looks like no one's here but Adrian. What can I help you with, Adrian? I don't have quite as much
I
time as I normally do, but I'll give you a little bit of time. I saw your message. I think you sent me an email, or it might have been a
Yeah, I
text
sent
message. I can't remember.
two. I sent two. One of them is the one we talked about with the big capital C,
Oh, right.
and the other one is probably the. I am severely behind because I thought I had one more day to do one graphic two. I did not, and I didn't even realize you had to do the online tests. I thought the online and face to face were two separate versions of the same thing.
No, the online is a version that hopefully gives you a little bit more confidence so you can do better on the face to face. But between the online tests and the practice tests, you should get ample, practice and therefore do better on
Oh
the
my
face to face test.
god. So I just straight up did not do the first online test. Oh my
Well, I will
god.
open it back up to you. I've had several students that missed it, so I'll open it back up to you and I'll give you like till
I
Sunday.
thought they were not required, and the only one that mattered was the face to face.
Yeah, I don't put assignments on my Canvas page that aren't required, except when I label them extra credit.
God. Oh,
So
oh
I'll
god.
set that up for you, and you'll have, like I said, till this Sunday to do it. But and I won't take off any points. But we all screw up. It's not a big deal. But just don't miss any more of them. I think you got
Okay.
another one due this weekend, if I remember
Yeah,
correctly.
the second test, which is what, chapters 4 to 6?
Yeah, actually, all of those are comprehensive, so it's 1 through 6.
I am not gonna under because I haven't even done 4 and 5.
Yeah, it's gonna be difficult for you, but you might want to have a come to Jesus
So
meeting and
can you
and
actually
do a
see the
buttload of homework.
so can you actually see the first question?
I was actually trying to pull it up on the email you sent me.
Yeah,
I got sidetracked talking to you.
a particle of mass initially at rest at position x equals 0 is accelerated by a force that increases in time as F equals capital C T times.
Oh, gotcha. I see it now. Yeah. FCT squared. Gotcha. So they're just telling you the force is proportional to t squared. That was exactly what I told you. I thought it was in lab, or in that class
It
you
was
gave us.
what exactly was C? I got
C
so
is
hung up
just a
over.
constant. It's just a constant. That's the way we separate. When you say F and T or thumbs up, you can write that as F is directly proportional to T with no equal symbol. That just has that little fish looking shape. But if you want to convert that little fish
Oh,
looking shape expression to an equation, then you replace the fish looking shape with a equals and you put a constant between the equals and the t. So F is directly proportional to t, thumbs up, means F is proportional to t, but it also means F equals CT. In this case, it's F is proportional to t squared, so it's F equals C times t squared.
oh my god. I thought I had it, which, oh god, I need to see my previous.
Mm-hmm.
CT, CT cubed divided by M. Yep.
Mm-hmm.
It's all of them involved a constant times T divided by M,
Mm-hmm.
which I did get. It was determined the velocity as a function of time.
Exactly. So let me show you what I'm thinking you're going to be doing on this part. Let me pull this open. You're still here with the. Uh,
Yeah, it's just this one was just determining functions, which I did not. The capital C is just a constant that.
so we've got
Oh.
F is equal to ct squared, which, like I said, it would start off as f is directly proportional to t squared. But in order to make that an equation, you say f equals, and normally we use k, but they were probably anticipating us using k for the spring constant, so they did that.
Oh,
So the summation of forces is equal to mass times acceleration, means in this case ct squared is equal to mass times a. So a is equal to c over m times t squared.
oh.
Your volume's coming in and out.
Further.
I don't know if it's my side or your
So
side.
I think it's mine. I have to decompose it one further because it says you need velocity. So I think you have to decompose A again.
Oh, let me
Uh,
look at the problem. It
oh no, you have
says
to take the integral of that, right?
well, it depends. Like the wording I'm seeing right now doesn't give me any information that's sufficient to jump to that conclusion. It says, I found chapter 4 problem I discussed in person, the one that got me to give up on the homework. A particle of mass m, initially at rest, x equals 0, is accelerated by a force that
They give you
increases
they give
with
you
time.
they give you two questions of it based around it. One of them is determine its velocity as a function of
Oh,
time,
okay. Yeah.
and the other
So
is position as a function of
gotcha.
time. Yeah.
With that, then we don't use a. That this is for when a is a constant. So what I'm going to do is say
Is that when you have to
what we're going to do is say f is equal to m dv dt.
oh,
So now we say t ct squared is equal to m dv dt. That means dv dt is equal to c over m times t squared. We can integrate both sides and multiply by dt on both sides. And in so doing, we just get v of t minus v0 because you're getting the integral of dv dt dt. That's just the integral of
uh,
dv, and that gives you v final minus v initial. I'm saying v final is v of t and v initial is v0. On the right hand side, though, we get c over m times the integral of t squared, which would be 1/3 t cubed. So now we can say the velocity as a function of time has got to equal 1/3 c over m t cubed plus v0.
oh oh, God. You just integrated again for position, right?
Yes, that's basically, yeah, you can now say v
Okay.
equals
Yeah, okay.
dx dt. That would mean dx
So
dt
so
is
I know you
equal
don't
to
have much
one
time,
third.
but I think I need to ask about the approach of the second question because I thought I got it. I didn't, and then I realized the graph is a little the
Gotcha.
vectors are a little off.
So it's the one that says a ball of mass m and it's got the vector and the circles and all that stuff.
Yeah, what concerned me was the diagram next to it,
Okay.
which I thought I understood the tangential acceleration to be the weight times the cosine of the angle. I thought it was just simply that.
The tangential acceleration. Uh,
Cosine theta.
well, the cosine is relevant because that does get you the component that's tangential, but that doesn't necessarily have anything to do with the overall acceleration. The acceleration, since it's going a circle, has to be v squared over r.
I wait. Oh, wait. What? Okay. No, I don't. I don't get it.
Okay, I'm trying to
I don't
read it right
immediately
now. It
get
says
it.
a ball of mass m equals 1.4 kilograms at the end of a thin cord of length r equals 0.85 meters revolves in a vertical circle about zero point 0, as shown in the figure. During the time we observe it, the only forces acting on the ball are gravity and the tension in the cord. The motion of a circular, yeah, excuse me. The motion is circular but not uniform because of the force of gravity. The ball
Yeah.
increases in speed as it descends and decelerates as it rises on the other side of the circle. At the moment the cord makes an angle of 40 degrees below the horizontal, the ball's speed is 6.5 meters per second. At this point, determine the tangential acceleration. Uh, at this moment, I just lost where I was. At the moment the cord makes the angle theta equals 40 degrees below the horizontal, the ball speed is 6.5 meters per second. At this point, determine the or the tangential acceleration A, and B the radial acceleration, and C the tension in the cord. Take theta increasing downward as shown.
I completely forgot there were moments of force.
Yes.
It's just that the vectors happen to be the same in the same direction.
Yeah, so we're saying this distance R is 0.85 meters. Oh, and we're saying the mass M is equal to 1.4 kilograms. We're also going a little further and saying that the angle theta is equal to 40 degrees. And of course, that gives us mg.
It gives us the components as well as the velocity at that instant.
Exactly. Like this. Excuse me. So these two vectors have to add up to give you mg, and this angle right here is also theta equals 40.
Oh no, the tangential acceleration is the same as the radial, right?
No, the tangential
Okay,
acceleration
yeah.
is the sort of the acceleration in the
Yeah, the
forward
dv
direction.
over dt.
And they got Ft here. That's the tension force. And the mg, of course, is 1.4 times 9.8. And that gives me 13.72 newtons. And we also know at this point the velocity is equal to 6.5 meters per second. So really all we have to do is figure out in some sense like an x and y component of everything. So I can actually put up a coordinate system right there as x, right there as y, and we can take the summation forces in the y direction equals mass times acceleration in the y direction. You can see in this case that x component, or using that x and y coordinate system that I chose, might not be that good of an idea because the tangential acceleration has to be, I mean, the radial acceleration would have to be broken into components in the x direction and y direction. So we're going to have an acceleration in both the x and y directions. That might not be the best coordinates, but it is a possibility. But you can also take that and say the summation forces in the x direction equals mass times acceleration in the x direction. And you've got to know that A has to be equal to v squared over r. That's the total acceleration has to happen. Okay.
But specifically no, that's just the general and not specifically the radial.
Yeah, that is the radial one for this one, but at all points. So that, I just wanted you to realize that that has to be true, or it can't go in a circle. So you've got to have that for the
Uh,
I'll say radial.
okay, yeah. If that acceleration equation is not true, then it's not in a circle.
Exactly. So that one's
Yeah.
got to be radially inward. That's why I was saying it might be better to use a different coordinate system. I was just showing you that we could do
Oh, is
that.
that? Oh, wait. So in this diagram, it's radially outward. Just oh god. I
Well,
think
there's
the
a component of mg that is fighting the normal force, or excuse me, that's fighting the centripetal force. That's
because
why they drew this little vector over here. Is that is the component of m that is radial, and this is the component of mg that's tangential.
yeah, what broke me was that the I think it was or the acceleration that you applied for was just not in the circle.
Right. So we might use a coordinate system like this. Maybe we could say this is our y prime coordinate system, coordinate, and this one would be your x prime. And then we could say the summation forces in the y prime direction equals mass times acceleration in the y prime direction. And in this case, it would be ft minus mg sine theta has got to equal m v squared over r. We have r, we have v, so we're all good to go on that. Then we also need the summation forces in the x prime direction equals mass times acceleration in the x prime direction, and that's the acceleration that they're wanting. That's the tangential one. So by using this coordinate system, you're actually dealing with it tangentially and radially. In this case, the only forces acting are the mg cosine 40. Actually, I'll write it as theta. Mg theta. That's the only force I see acting in that x direction, and that has to be equal to m times a tangential. Notice I just changed it to a sub t just to remind you it's tangential. It's still the same thing as it was before, ax prime. It's just that's that. So you can now say that at has got to equal mg cosine theta. So your answer should just be the 100 or 13.72 times cosine 40.
Oh,
That gives me
I
10.51.
I don't think I even got remotely close to the. Oh wait, you said 10.5. I
Yeah,
think I got a.
10.51. Yep.
I think I believe I got a less precise answer. I have to double check.
And
Uh,
we should be able to figure out everything else. What all did it ask you? I'm trying to remember.
it's all in the it was all
The
in the
tangential
question. Yeah,
acceleration. So that
the
should be the
radial.
tangential acceleration, be the radial acceleration. So in this case, the radial acceleration is just going to be ft minus, or excuse me, if I divided through by m, it would be ft over m minus g sine theta. So you just got to solve for ft and then subtract from that mg sine theta and then divide that by m, and that'll get you the tangential acceleration, or excuse me, the radial acceleration. That's going to be ft over m minus g sine theta. So what you have to do first, of course, is to put in the v squared over r, but you could also just say a radial is equal to v squared over r. That should work as well. And for instance, in this case, it was 6.5 meters per second, if I remember correctly. Yeah, 6.5 squared divided by 0.85. That gives me 49.7.
And that's just the radial.
Mm-hmm. So that should be enough to at least get you started on what to do, if not completely done it. But anyways, any questions on that?
Sine. So f of x. So it's just take the second wall, expand the two.
Yeah, and you can see like the way I wrote a radian, that can be solved for FT, and then you'll have the tension in the rope because you know G, you know theta, you know M,
I
you
don't
know
know how you
A
cancel out the
radial.
M. I
Yep.
don't know how you canceled out the M in the tangential.
That just well, the M was on both sides, so mg cosine theta equals ma. You can divide both sides by m, and that just gives you g cosine theta equals at.
Yeah. Okay. Uh,
Oh,
okay.
that's
Yes.
why I wrote it wrong.
Yeah.
That's I see
Uh,
what you're saying.
yep.
Sorry about that. Yeah, it's
Yeah.
just g cosine theta. Uh,
Okay.
Now I got to figure it out if I. Oh, and that's a problem because I was supposed to divide through by m. So let me correct that figure. So a tangential is supposed to be g cosine theta, which should be 9.8 times cosine 40, and that gives me 7.50, actually 7.51 meters per second per second. So that's all you got to do. Remember, you got to use your coordinate system. You got to make a coordinate system so you can have an x component and a y component. You have to use Newton's second law for the x direction, Newton's second law for the y direction, and then try to use your math to solve for the unknowns. That's pretty much it.
Okay. Uh. Okay. Uh. God, I'm not gonna have a fun time in the next 4 days. Next two, not for sure. Uh,
Don't dilly dally. Don't obsess over little things like I don't know what FT means or stuff like that. What you want to do is just sit down and start solving problems, preferably by the practice test. So just jump into the practice test. If you find that you don't understand something, maybe find a similar homework problem and try to work that because it'll have hints and stuff like that. Or just Google it. You can find places where they've explained how to solve various problems. So if you just find a similar problem, you look how they solve it, and you do that again, and
hmm,
then you bring it back and apply it to your problem.
okay.
But yeah, try to focus more on the practice test as opposed to the homework. I would definitely rather you take the practice test, 12 times and take a zero for the homework than to get 100 on the homework and only take the practice test two times.
Okay. Practice test with book. Okay.
All right. Well, I got a split, man. I got a bunch of tools set outside, and I need to get going in
Yeah.
real quick. But you did good. I will try to go through and answer these questions. I found all four emails you sent me, so I'll try to address that. I probably won't do it tonight, but I'll do it tomorrow for you.
Oh
Okay?
yeah. Oh yeah. Did you ever get the answer to the third law of motion if it requires an inertial reference frame?
Yes, it is not valid in a non-inertial reference frame.
So yeah, all three need inertial.
Yep.
Got it. Okay.
All right. Well, I'll let you go, bud. And like I said, you're doing good. Just keep on pressing on. But I'll try to send you an email tomorrow or something with some answers for those problems. And if need be, we can make a Zoom meeting and you know get together and discuss it.
Yeah.
Okay?
Yeah. I asked for an appointment for a Zoom meeting. So yeah.
Gotcha.
Okay. Yeah. Thank you.
All right. Well, have a good one, Adrian. Bye bye, everyone. I don't think Gabe's still here. Bye, everybody.